series on electromagnetic waves. So today we'll start with the module number 2, lecture number 21. So the contents covered in the previous class were a potential difference, potential, and we also have seen about the potential due to a system of charge, and then we have seen a problems on potential difference and the potential. Okay, so in this class we'll try to cover about what is potential gradient, and we'll try to see problems on the potential gradient. Okay, so before that, let us try to solve one more problem. In the previous class we have solved the problems on potential and potential. We have solved the problems on potential for a different case due to a point charge, and in this class we'll try to solve the problems on the line charge. So this example number 8, they have given a line charge which is placed, actually it is parallel to the z-axis, and it is being given as y equal to 1, z equal to 1. Okay, carries a uniform charge 2 nanocoulomb per meter. So this is rho L is equal to 2 nanocoulomb per meter. And we have different conditions saying that if v equal to 0 at origin, find v at 5, 0, 1. That is, at point A, we need to find a potential due to a line charge. Next, they have told that v is equal to 100 at this point defined as 1, 2, 1. Then find what is a potential at a B point. Okay. So first thing, let us try to understand how this line charge is placed. Okay. I found many students get confused with this particular thing. So first thing we need to understand, this line charge is parallel to which axis? So please do remember, this particular point are also useful whenever you are trying to solve the problems on the line charge in the module 1. It is finding electric field. Okay. First thing, try to understand the line charge is parallel to which axis? Okay. Parallel to which axis? Okay. Now you could see that they have given they have given that y is equal to 1 and z equal to 1, which means that you can find that the missing variable is x. So it means that the first thing is line is parallel to the x-axis. Okay, and next what they have given is, that is, y is equal to 1 and z equal to 1. Okay, from this point you draw a line parallel to the x-axis. Okay, now what does it mean that on this line, okay, on this line, okay, the only variable is the x-axis. Okay, the remaining y and z are fixed. Y is 1 and z is 1. Okay, so every point on this line I can represent it as x comma y x comma 1 comma 1. Okay, this 2 y and z are constant. The only variable is the x1. Okay, so please note down this. Okay, the missing variable, okay, will be a parallel to that axis. If x is missing, it means that it's parallel to that missing variable. Okay, missing variable axis, you can say. Okay, and next thing, you should try to also understand that, okay, if it is parallel to the x-axis, it means that the remaining 2 y and z will be constant, and the only variable will be the x1. Okay, yeah, this informations are really useful to find a perpendicular distance. Okay, okay. So with this understanding, let me proceed to find a potential field. Okay, yeah. So now you could see that in order to find the potential due to this line charge, we'll try to use the most general formula of potential. We know that potential is given as a minus line integral of E dot dl, okay, and plus C. This is plus C has come into picture because I'm not trying to show any limits. Okay, I'm not trying to solve like a definite integral. Okay, so we don't have information about the initial point and the final point. Okay, yeah. So in that case, really we can take up this formula saying that v equal to minus integral of E dot dl plus C. Okay, yeah. So the dl is a very general differential length. and we are in, we know that this problem is in, works better in the cylindrical, so I'll choose the DL, DO arrow hat plus rho d phi a phi hat plus dz az hat. And also I know what is the electric field due to a line charge. Okay, and we know it's a function of rho alone. Okay, and it points in the direction of arrow hat. Okay, so I know what is electric field due to line charge, which is given by like rho L divided by 2 pi epsilon into 1 by rho arrow hat, and I have chosen this DL. Okay, when I do a dot product, I'll retain only this term, that is rho L by 2 pi epsilon 1 by rho d rho. Okay, yeah. So now we'll try to, now you could see this is actually like indefinite integral. Okay, we don't have any limits. Okay. So you could see this rho L by 2 pi epsilon is everything is constant. And we know that the integration of 1 by rho d rho, 1 by rho d rho is equal to ln rho. Okay, ln rho plus c. Okay, plus c. Indefinite integral. Okay, so now what I can write now, v equal to minus rho L by 2 pi epsilon ln rho plus c. Okay, yeah. So now you could see in this problem we have derived this. Okay, you can really remember this result. Okay, it is it is quite worth of remembering this result, as we know the potential due to point charge is q divided by 4 pi epsilon r. Okay, and where r is a distance between the point charge and the field point. Okay, similarly you can really remember this expression. This is a potential due to a line charge. Okay, and in more general we write even this as q divided by 4 pi epsilon by r plus c. Okay, so this particular expression of potentials are useful whenever they have given the reference point as indirectly or indirectly, like something like this. Okay, the potential is they try to give some intermediate value of the potential. Okay, yeah. So we got to know what is we got to know this result. So now first thing we need to find c. Okay, now to find we'll try to solve first part A problem. Okay, and in that first thing we need to find c. Okay, now how do we find c is, it's given that v is equal to 0 at origin. Okay, so this information is useful to find the c because we know the potential. Okay, so now you could see in order to find c I should try to compute what is rho now. Okay, and we know what is rho from an electric field. It is a perpendicular distance from a line charge to a given point. Okay, now what is given point to us? The given point is, or we could say field point, it is the origin. Okay, so the perpendicular distance between line charge and origin is quite simple. It is field point minus the source point. Okay, now you could see on the line charge. Okay, you could see on the line charge I have denoted the points as x comma 1 comma 1. Okay, anyway these two are constant. The only variable is x. Okay, now to find a perpendicular distance we should choose the value of the x which is same as the field point. Now you could see that the field point value is 0. So I should choose my x values also as the 0 one. Okay, so with this I can really find the perpendicular distance. It is 0 minus 0, 0 minus 1 is minus 1, and 0 minus 1 is minus 1. So its magnitude, because anyway I'm interested only in the magnitude. So its magnitude is √2, which is same as the rho. Okay, so I got to know what is rho here. So rho is √2. The potential, the potential for this particular information, it is 0. So which is 0, and you substitute what is rho L at 2 pi epsilon into ln √2. You could see that the c value will be 12.45. So you could see that this information is useful to find the value of the C. Okay. Yeah, but the actual thing what we need to find is the potential at this point A. Okay. So now what we do is we take up this expression, that is V equal to minus rho A by 2 pi epsilon ln rho. We got to know what is the C now. The C is 12.45. Okay. Yeah. So now what we need is, now you could see in order to find V at the given point, again I need the one more thing is rho. Okay. But now this rho is a perpendicular distance between line charge and the given point A. Okay. And what is the point A now? The A is 5, 0, 1. So what we can do is, again we can find perpendicular distance. We know it is always a field point minus the source point. The field point is given as 5, 0, 1. Source point is nothing but on the line charge. And you could see on the line charge I have defined the points as x, 1, 1. Now the question comes is what x I should choose, and I said that we should choose the value of the x as same as the x value of the field point, and you could see that it is 5. Okay, so this is important. I hope you remember these things. So now 5 minus 5 0. You could see 0 minus 1 is 1 and 1 minus 1 is 0, and hence the magnitude of this one is 1. The perpendicular distance magnitude is 1, so rho is 1. Okay. So if you try to plug in that, you could see that ln of 1 is 0. And hence the potential is 12.45 volts. Okay. Yeah. Yeah. Okay. So any doubts with this A part of the problem? Yes? Any doubts? Yes? Am I audible?
Yes, sir.
Yeah. So any doubts with this problem?
No, sir.
Okay. So
No,
we'll
sir.
continue with the B part. Now, what is given in the B part? It is given that V is equal to 100 at 1, 2, 1. Okay. Sorry, here is the question. The B part is if V equal to 100 at 1, 2, 1, find the potential at the B, that is minus 2, 5, 3. Okay. Yeah. So now you could see that again we have to use this particular same formula. Okay, and we know that the first thing we need to find the C. Okay, the first thing we need to find the C. Okay, now to find the C, you could see we know what is V because it is given that V is equal to 100 at this point. So only one thing is we need to find now rho. Okay, so in this case, what is rho? Rho is a perpendicular distance between the line charge and the field point. Okay, so now anyone could tell me how do we can find the perpendicular distance? Yes, or anyone could tell me it is. I mean, anyone could tell me it's a perpendicular distance between line charge and which point in order to find a C? Yes. My question is, in order to find C, okay, as I told that we need to find the perpendicular distance. Now, in order to find the C, we should find a perpendicular distance from a line charge, that is for sure, to a which point? To a which point? So in a B part question, we have two things. One point is 1, 2, 1, and one more is minus 2, 5, 3. Now I should say that perpendicular distance between 1, 2, 1 to find a C, or it is a perpendicular distance between a line charge and the B point. Which one? Yes? Anyone? So anyone could tell me it should be between which points? Yes? Yes, anyone? Anyone please could tell me that? Yes? Am I audible?
Yes, sir.
Yeah, so please can you tell me in order to find a C, I should find a perpendicular distance rho. Now it is between 2 points. Yes, Vani? Yeah, please anyone tell me quickly. So Vani is absent. Vanita?
No. Yes, sir. Between line charge and
Yeah, between line charge and which point? There are 2 points in the B part. 1, 2, 1, and one more is minus 2, 5, 3. Which one?
1, 2, 1. 1,
Yeah,
2,
that's good.
1.
It is, yeah, it is 1, 2, 1. That's good. Okay. If that is the case, then what you could see on the line charge, I have defined a point as x, 1, 1. Now, what should be my value of the x now? What should be the value of the x?
1.
Yes, it should be same as the field point x value. Okay. So the x value should be as the 1. Okay, yeah, that's good. So you could see that's how I found the perpendicular distance. The field point is 1, 2, 1, and this is a source point which is x, 1, 1, and I've taken the value of the x as 1. And you could see the perpendicular distance will be again as a 1. So rho will be 1. So ln rho is 0. I'm sorry, I mean ln of 1 is 0. So the C value is 100. Okay. Yeah. So now we got to know what is the value of the C. Okay. So now next thing is we need to find what is the potential at this given point B. Okay. So we can do that. Again, we have to use this particular formula, that is minus ln minus rho L by 2 pi epsilon ln rho plus C. Now we got to know what's the value of the C as 100. Okay, but now only thing is we need to find what is the perpendicular distance. So now it is a perpendicular distance between the field point and the line charge. Okay, and the field point now is B. Okay, that is minus 2, 5, 3, and this is actually x, 1, 1, and I should choose x same as the field x, I mean field point x value, which is minus 2. And you could see the rho will be root 20. If you plug in this value and if you try to solve this, okay, you'll get the answer as 46.15 volt. Okay, so that is the potential. I mean that is a potential due to the line charge for different condition. Okay, so you could see in the first case they have given the 0 reference point. Okay, so this is an important point to observe. In the A part they have given a 0 reference point. Okay, whereas in the B part they have given some intermediate value of the potential. Okay, so whenever we have such thing, we can really use this particular expression. Okay, so everything, I mean, every time it is not necessary to derive this. You can really remember this formula. As I told you that, as we can remember the formula for a point charge as Q divided by 4 pi epsilon R plus C, you can really remember this particular formula. Okay, so with this, let us now begin with a new topic uh, called as a potential gradient. Okay, yeah. So in this topic, we'll try to derive, I mean, the relationship between what we say is V and E. That is, given potential field, how we can find the E field. Okay. So we know that given E field, we can find a potential field that is fine. That is what is known to us. That is V equal to minus integral. I mean, like it's a line integral of E dot dl. Okay. So my next question is it possible to find an E field given potential field? Okay. So let us see how we can do that. Okay. So we know that V is equal to minus minus line integral of E dot dl. Okay. So we also know that the incremental potential difference is given by delta V equal to approximately equal to minus E dot delta L. Okay. In above equation, we assume that E is constant over length L because the delta is really very small. Okay, and we can think that E is constant over that length. And delta V is the incremental potential difference between final point and the initial point of delta L, as shown in the below figure. Okay, so what I'm trying to say for example, this is the I mean, in some region, this is the electric field lines. Okay, and say that you are interested to find what is the potential difference between this point and this point. Okay, between this initial point and that final point. Okay, I can say this as A and this as P. Okay, or as we have a convention saying that we choose initial point as B. Okay, and this as A. So I'm interested to find what is VAB, the potential difference between A and B. Okay, and this potential is like a delta V. It is a small incremental potential. Okay, and we know it is given by minus E dot delta L. Okay, we don't require any integration to perform this as we have here, because we know that over this very small length, okay, E is really constant over there. Okay, so yeah, so now you could see that this is the electric field and this is my displacement, or you could say this is my path. Okay, and the angle between them is theta. If that is the case, you could see from this above, from above figure, the equation 2 can be written as delta V is approximately equal to minus E into delta L cos theta. Okay, or I can write it as minus E cos theta delta L. Okay, and we know what is E cos theta. E cos theta is a scalar component of the electric field along this delta L. Okay, and we say that this component is really constant over that delta L. Okay, yeah. So with this understanding, I can say that, so let us pass a limits. That is, we'll try to allow this delta L is as small as possible. If that is the case, we can write the equation 3 as dV by dl is equal to minus E cos theta. Okay. So we got this relationship, we got this equation dV by dl equal to minus E cos theta. Okay, yeah. So now from here, okay, we are going to ask one question, that is, Let us check in which direction should delta L be placed, okay, to obtain maximum value of delta V. Okay. The question is, for this figure, we can ask a question. Okay. Now, in which direction delta L should be pointed? Okay. So that we get a maximum potential difference. Okay. So you could see that when theta is 90 degree, okay, I'm sorry, yeah, when theta is 90 degree, we know that the potential difference will be like a zero because no work is done because theta will be equal to 90 degree. Okay, so we cannot really place along this. We cannot really place along the direction of the electric field because we know that. In order to do a work, okay, we should be always and against the field. Okay, yeah. So you could really see that. Okay. So what I can say that if I am referring to this equation 3, okay, so I say that delta L is a constant, okay, that cannot be varied. Okay, for a given path, delta L is a constant, and E also has a definite value at the point which we are working. Now you could say that the only variable is the direction, that is AL hat. Okay, and from equation 3, it is really clear that when cos theta is equal to -1, okay, when cos theta is equal to -1, you could see that the potential difference will be maximum. Okay, the potential difference will be maximum. Okay, and if you try to see when cos theta is equal to -1, what does it really implies that? It implies that it implies that the direction of the delta L should be opposite to the direction of the electric field. It should be opposite to that one. Okay. So from equation 3, we can say that delta V is maximum when cos theta equal to -1, or delta L points in the direction opposite to the electric field. Okay. So now what we can say is dV by dl is maximum is equal to E. Okay, which means that we got to know what is the magnitude of the electric field. Okay, the magnitude of this electric field is nothing but dV by dl maximum. Okay, so with this small exercise, okay, we got some good information. Okay, now what is that? The above information shows two characteristic, okay, of the relationship between E and V. Okay, the first thing, the magnitude of the electric field. So that is what we have here. The magnitude of the electric field is given by maximum, okay, maximum value of the rate of the change of potential with the distance. Okay, this is really interesting. I'll try to repeat once again. What does it says that? Okay, from this relationship, what we can say is the magnitude of electric field is given by the maximum value of the rate of change of potential with distance. Okay, it's a maximum rate of change of potential with respect to the distance. Okay, so we got to know what is magnitude of the electric field. Okay, now what is should be a direction of the electric field. Okay, so you could see that I could say yeah, uh, this maximum value is obtained when the direction of the distance increment is opposite to the electric field, or I could say that the direction of the electric field is opposite to the direction in which the potential is increasing the most rapidly. Okay. Yeah. So now from this we got to know the two things. Okay. One is how should be the magnitude of the electric field. Okay. It's a maximum rate of change, and the direction of the electric field is opposite to the it's opposite to the point where the potential is increasing rapidly. Okay. Now we can try to understand these 2 points by referring to this figure. Okay. So this figure is, this figure describes the potential field in terms of equipotential surface. Okay, so this is the potential field defined in some region, and this lines, okay, trying to tell these are the equipotential surface. Okay, or you can say equipotential curves. It means, at every point on this curve, the potential is plus 10. On this curve, the potential is plus 20, 30, 40, 50, and so on. Okay. So here is the, let us, in this particular potential field, let us take the point P. Okay. And I'm going to ask a question is, that is, what will be the electric field at this point? Okay. So now by referring to this 2 points, okay, now I know that the magnitude of the electric field, okay, the magnitude of the electric field is maximum, it's given by the maximum rate of change of the potential, okay. And you could see that from this figure, okay, it is in this direction, the potential is increasing, okay. So what I say that as starting at point P, okay, we lay off a small incremental distance delta L in various direction, hunting for that direction which the potential is changing most rapidly. Okay. So at this point, I've been asking a question is in which direction I should point so that I get the maximum rate of change of the potential. Okay. So you could see that towards the right side, it is actually like decreasing, and you could see towards the left side, it is really increasing, and it is increasing perfectly little upwards. It is left and little towards the upwards, so that I can reach to this maximum potential. Okay. That's what we say from our figure. It is clear that it is towards the left side and slightly upward. Okay. Yeah. From this, we come to know that is, we come to know what is the magnitude of the electric field, okay, which is given by the maximum rate of change of the potential. Okay. So the next thing is about direction. Okay, what is the direction of the electric field? So it's quite simple. The direction of the electric field will be opposite, okay, is opposite to the where the potential is increasing most rapidly. It is increasing in this way, so the direction of the electric field will be in this way. Okay, so we say that the direction of the E field is oppositely directed to that right side and it's slightly downwards at P. Okay, yeah. So we got to know this information, okay, and relationship. Okay. Now, as I said that these are the equipotential surface. Okay. Now, what we say is, let A n hat be a unit vector normal to the equipotential surface. Okay. And you could also see that, these unit vector or normal to this surface or normal to this equipotential surface are actually directed towards the higher potential. Okay. Because on an equipotential surface, okay, if you try to go in this way, okay, if you try to go in this way, the potential difference will be zero, because at all these points on the equipotential surface, the potential are the same. Okay, and obviously the potentials are zero on this surface. Potential difference will be zero, because on this surface, all the points have the same potential. Okay, so which means that, okay, the unit vector normal to the surface will be trying to direct, okay, towards the increasing the potential. Okay, so this is quite important observation, that is unit vector normal to this equipotential surface, okay, are directed towards the higher potential. Okay. So if that is known to us, now I can write my E as E equal to minus dV by dl maximum, okay, with minus an hat. Okay, so this gives us the magnitude, okay, and we know that an hat is pointing towards an increasing direction of the potential. Okay, and minus a n hat obviously will point towards the what we could say as I mean it will point exactly opposite, okay, to the increasing potential, okay, and minus a n hat will be the direction of the electric field. So this is magnitude and this is the direction, okay. So with this, what we can say that we got to know, I mean, the physical interpretation, or we got to know, we got to know what is the process to find the relationship between the this electric field and the potential. Okay. Yeah. Okay. So now what we say is the equation 6 and 8 provides a physical interpretation, or a physical interpretation of the process of finding E from V. Okay. Now what is something interesting is the procedure leading to V from V to E is not unique to these pair of the quantities, that is potential, that is V and E. However, okay, but has appeared as the relationship between scalar and vector field in many other disciplines like hydraulics, thermodynamics, okay, and almost every field to which the vector analysis has been applied, okay. And the above process obtaining E from V is known as a gradient, okay. The process what we have seen, okay, to find the relationship between V and E is known by a gradient, okay. So we define the gradient of a scalar field T, okay, gradient of T as, which is denoted as a gradient of T or a gradient of T as derivative of T with respect to N, okay, A n hat, okay, where A n hat is unit vector normal to the equipotential surface, and normal is chosen which points in the direction of increasing values of the T, increasing values of the, okay. So with this new term, I can write now electric field as E equal to minus gradient of V, okay, yeah, minus gradient of V, okay. So this is what we have seen. So far, whatever we have seen is actually a physical interpretation of a process of finding V, finding E from the V. Okay. So if you have any doubts, so please let me know till here. Yes, any doubts? Any doubts with any points which we have discussed so far? Okay, so so if that is clear, okay, so you could see we got some physical interpretation, okay, we got to know the process, okay, and from all these things, okay, what we come to know that, okay, the magnitude of the electric field, okay, is given by the maximum rate of change of the potential, okay. So if you have really a potential field, okay, you should go. You should try to move in the direction where the potential is increasing. Okay, we need to find the maximum rate of change of the potential. Okay, and the direction of the electric field is given exactly opposite to the where the potential is increasing rapidly. Okay, this is what the information we have obtained. Okay. and this particular thing, okay, is being applied in many different discipline, and it has got the name as gradient. Okay, so if you ask me what's the gradient of a scalar field, okay, I mean from a mathematics point of view, okay, if you ask me what is the gradient of I mean what's the gradient of a scalar field, okay, and here we have taken it as t, we write it as dt by dn. Okay, now question is what is this an hat? Okay, an hat is unit vector normal to the equipotential surface. Okay, and we should choose this normal, okay, which points in the direction of increasing the scalar field. It is t. Okay, this is how it is defined in general. Okay. Okay. So next thing is, I mean, we need some formula, okay, or we need some expression, okay, to compute the electric field from given a potential field. Okay. So in order to complete that, so we know that the total differentiation is defined as dV, total differentiation, which is dou v by dou x dx plus dou v by dou y dy plus dou v by dou z dz. Okay, and also we know that dv, okay, we can write it as minus e dot dl. Okay, and we know dl, I mean in the rectangular we can take it as dx ax hat plus dy ay hat plus dz az hat. When you do a dot product, it leads to this one. Okay, now you could see that equation, this is actually 10. Okay, so equation 10 and 11 are true for any dx dy dz. Okay, so by comparing this 10 and 11, I can say that Ex, okay, is equal to minus dou v by dou x, Ey equal to minus dou v by dou y, and Ez equal to minus dou v by dou z. Okay, now combining these above results and writing it vectorially, okay, I can write the so it means that I got to know what is the x component of electric field, what is the y component of electric field, and what is the z component of electric field. Okay, with this two simple equation, I got to know this is the relationship. It says that you should take a potential field, okay, make it differentiation, that is, make it as a partial differentiation of v with respect to x, you will get the x component. Take the potential field, complete potential field, do the partial differentiation with respect to y, you will get the y component. Okay, do a complete partial differentiation with respect to z, you will get the ez component. Okay, so once you know these components, we can write it as vectorially as ex ax hat plus ey ay hat plus ez az hat. And what is ex? It is minus dou v by dou x. Taking this minus sign common, we can write electric field as dou v by dou x ax hat plus dou v by dou y ay hat plus dou v by dou z az hat. Okay, yeah, now this is what we got an expression, okay, to compute the potential field, I mean to compute electric field for a given potential field. Okay, the above expression will help us to evaluate the gradient in rectangular coordinate. Okay, so we can really recall the vector operator. Okay, this particular thing we have seen in I mean we have seen this thing when we were trying to define divergence. Okay, the vector operator delta is given as dou by dou x ax hat plus dou by dou y ay hat plus dou by dou z az hat. Okay, so if I try to see this equation, okay, and if I try to this one, so you could see that I can really write E as del V. Okay, you could say that something multiplying the scalar V. This is a vector, okay, and you multiply with a scalar V. You could see that you will get this particular E. Okay, so del V is nothing but dou V by, this is a del, you multiply with a V, so it will be simply like dou V by dou x ax hat plus dou V by dou y ay hat plus dou V by dou z az hat, and this is nothing but gradient of V. Okay, and we know that E equal to minus gradient of V. Gradient of V is same as delta V, so I can say that E equal to minus del V. Okay. So as you remember, we write rho V divergence is equal to del dot D. Okay. So we say E equal to minus del V. Okay. Yeah. So we got to know what is E equal to minus del V. That's a gradient in the rectangular. We also need the gradient in the other coordinate system, that is in the cylindrical and spherical. It is given by dou V by, in the cylindrical it is given by dou V by dou rho, and dou V by dou rho arrow hat plus 1 by rho dou V by 1 by rho into dou V by dou phi a phi hat plus dou V by dou z a z hat. Okay. Similarly, in the spherical coordinate system, it is given by dou V by dou r ar hat plus 1 by r into dou V by dou theta a theta hat plus 1 by r sine theta dou V by dou phi a phi hat. This is in the spherical coordinate system. Okay. So remembering this particular gradient, okay, is quite simple as compared to divergence. Okay. You could see this in all these three things. Okay. This dou V ax hat plus dou V a y hat dou V plus dou V az hat is really common. Okay. These numerators, these denominators, okay, which I'm trying to show here, are nothing but the differential lengths in those particular coordinate system. Okay, so differential length in the along x is dx. Okay, it's a dx, but only thing you should remember, you should write it as a dou x. So differential length along y is dy, you should write it as dou y. Differential length along z, it is actually dz, you should write it as dou z. Now, if you remember in the cylindrical coordinate system, the differential length along, arrow hat is like d rho, okay, and here you should write it as dou rho. And if you remember what is the differential length along a phi hat is rho d phi, okay. Here we should write it as rho into dou phi, okay. So here we have quite of a hint to remember this gradients in different coordinate system. Okay. Yeah. So this is all about gradient. Okay. Yeah. So if you try to observe some textbooks or author, okay. In order to derive the relationship between an electric field and the potential, they will start from here. Okay. You could see if you start from here, we get the this particular mathematical expression. Okay. Yeah, but if you really start from here, but we'll never come to know what is the meaning of the gradient actually. Okay. Okay. So that's the reason it's a really good thing to start from here. Okay. Okay. We'll come to know the physical interpretation. Okay. And we'll come to know what is the exactly the gradient is. Okay. Okay, so with this, we'll conclude this class with one problem. Okay, that is example number 8. Okay, now given potential field V equal to 2x square y minus 5z. Okay, and a point P that is given as minus 4, 3, 6. Okay, we wish to find several numerical values at point B. They have given a potential field and they have given this point P. And now at this particular point, we are interested to find many, we are interested to find many different values. The first thing is the potential V, the electric field, the direction of the electric field, flux density, and the volume charge density. Okay. So the A part, we need to find the potential at this point P. This is quite simple. We have to substitute the point P in this given expression. And it is just, you can check it out that if you really substitute this, this x as minus 4, y as 3, and z as 6, you will get the answer as 66 volts. Okay, yeah, which means the potential at that point is this much. Okay, so next we need to find an electric field, okay, at this point P. So first let us find the electric field, and we know the potential is given in the rectangular coordinate system. So I should use the gradient in the rectangular coordinate system, E equal to minus del V, which is given by minus of dou V by dou X AX hat plus dou V by dou Y A by hat plus dou V by dou Z AZ hat. Okay. Now let us try to find one by one. Dou V by dou X, it means that I should take complete potential field and I should make a partial differentiation with respect to X. You could see if I do a partial differentiation with respect to X, it will be 4xy. This will be acting as a constant, it will be 0. Okay. Similarly, partial differentiation of V with respect to Y will be 2x square. Okay, and similarly, partial differentiation of V with respect to Z will be minus 5. So you can really plug in all these things and we can write the electric field as this one. And if you substitute the point of x, y, you will get the electric field at that particular point. Okay. The C part was to find the direction of the electric field, and in order to find direction of electric field, we know that it is given by the vector divided by the magnitude. This is the magnitude, which is square root of 48 square plus minus of 32 square plus 5 square, okay, which leads to this one. If you divide this vector divided by magnitude, you will get the direction of this electric field. Okay. Okay. And next we need to find D field. We know that given E field, we can find the D field. So the D field at that particular point is, you multiply this particular E field with the epsilon naught, you will get the D field. Okay. So next thing was to find rho V. Okay. And we know that rho V is del dot D. Okay. You have now D field. We should do now del dot D. Okay. And we know that del dot D is dou dx by dou x plus dou dy by dou y plus dou dz by dou z. Okay. Whereas dx is this one. Okay. So the partial differentiation of that with respect to x will be minus 35.4 y. Okay. And you could see the rest of what we say is dy and dz. Okay. Dz, you could see that dy is a function of x alone and dz is a constant. So if you try to make a partial differentiation of this term with respect to y, will be 0, and similarly with respect to z, this term will be 0. So as an answer, you have only minus 35.4 y picocoulomb per meter cube. Okay. And if you substitute the value of the y, you will get this as the answer. That is, charge density at that point is minus 106.2 picocoulomb per meter cube. Okay. So as a practice problem, you can try to solve. I mean, everyone should solve the drill problem 4.8 from Head and Kimmerly. Okay, Head and Buck 8th edition 4.8. Okay, so this is all for today's class. And you could see in today's class we have discussed about the potential gradient, and we have solved the problem on the potential gradient. Okay. So all the contents in this lecture requires applying the concepts of work done, differential length, line integral. Okay. So this entire lecture comes under the Bloom's level 3. Okay. Mapping to the course outcome 2. Okay.